In this video, we're going to go over the main structural forms and connection types which are defined in the New Zealand Structural Steel Standard NZS 3404. And these are going to be important for us understanding some design implications, particularly around bending and on our compression design and for our design of second order effects. So getting into this, let's first just start looking at structural forms. So there are two main structural forms, one being a sway system and one being a brace system. So with a sway system, it's really the bending capacity and the stiffness, the rotational stiffness of the columns and the beams, which resist deflections. The columns are not restrained, so they're effectively allowed to sway, and failure will happen at each story. In a brace system, the column ends are effectively pinned and restrained, and they can't move side to side, and then failure is going to be at a member level. And so these are sort of the definitions within the standard, and these images come straight from the standard as well. But I always found when I was first introduced to these, this is a little bit vague and a little difficult to understand. And so I always thought it's better to think about them in terms of these effects of Pdelta. So what a Pdelta moment is, these are also termed second order effects. It is an additional moment due to a deflection. So it is a nonlinearity which occurs in your structural response. However, we account for it through some linear procedures. So we have basically two types. We've got P big delta and P little delta. So for P big delta, say I've got this cantilever column here, and I'll draw the deflected shape. Well, if it has a force P coming down, well, it's going to have some eccentricity from the center line and where the reaction is of delta. And so, you're going to have a resultant force, because some of the forces in the y have to equal 0, P. And then there's also going to be a moment, so this is generating a moment this way, trying to push it down. And so, well, we need to resist with a moment the other way of P delta equal to M. And so this is what's, it's our sort of big P big delta, which comes in where we've got the ability for the top of the column to move relative to the base. That's what you'd see in a sway system. Now, P little delta is whenever it is going to be the deformation sort of within the length of a member. And so what I've drawn here is a sort of pin and roller column, and say it's loaded axially with a force P. Well, it's going to deflect sort of within here some distance little delta. And if we took a free body diagram and we take a cut through here, well, we would see there's a P here, and again there's a small moment of M equal to P times little delta. So we see this within a brace system as the dominant sort of P delta second order effects. It also occurs in a sway system. And that's because, so if we look at sort of the P delta here, well, there's going to be some deformation, little delta there as well. Now, the thing to keep in mind is that for, these sway systems where it's P big delta, it's really this large sort of top deformation. It's going to be so much bigger than this one, so we can effectively ignore this when we're looking at a sway system. We need to account for it when we're looking at a brace system. And so just looking at some of this very simplified versions of our second order effects of P big delta, P little delta, let's see how they occur kind of within these two systems. So I have two drawn here. So we've got our sway system where, say we've got some forces, some from an earthquake pushing this way. Well, we're going to get our frame deformation here, and we would have some gravity load on each of these columns. And each of these is going to have, some distance delta story to story. And this is why, because it's the swaying of this entire story over that is going to mean that we're in a sway system, we're going to fail sort of story by story. And so that's when we design it, that's how we do our check. We look at what our stiffness is and our deflections over, for a per story basis. Now convert that, contrast that to a brace system, and I've drawn the earthquake forces going the other direction, so the braces are in compression here, and you'd see, we've got our little delta here. So we can still buckle, but we're not buckling over the entire story, we're just buckling over the member, which is going to be in compression. Now, another important thing to note with a brace system, so what I've drawn here on the sway system, obviously no braces anywhere within there. It's a, say, moment resisting frame. Now with a brace system, you just need one bay to be braced. So you don't need to have each bay be braced for it to be a braced system. You just need your load path to have some point where you are restrained from moving that column. So, if we're pulling on here, we'd have our forces coming through there, forces coming there. Well, then the top of this column is actually restrained by that brace, and because all of these are linked together, well, these two columns are also restrained by that brace, and so on up the entire height, and that's why we're looking at this as sort of a member-by-member failure. So going back to our definition, here we can see that that sort of makes sense, where we're looking at story-by-story failure for a sway system, the column heads are not restrained, and then for a brace system, the column ends are restrained, and so we're looking at the failure of these members. Now, what would these systems actually look like instead of these drawings that we have here? Well, I've got a couple examples here. The one on the top is a moment resisting frame, and you could actually quite clearly see how that would sway from side to side. Because there's no braces there, and so it's really just the rotational stiffness of the columns and the beams which are really restraining this element. And then down at the bottom we have a brace system where these are some buckling restraint braces, and again quite common sort of structural system. So moving from structural forms to how we actually connect members together, we have three main connection types which are defined in NZS 3404. These are a simple connection, which is free to rotate, a semi-rigid connection, which can carry some moment across it, but it is not going to have the same moment capacity as the sort of beam which it's connecting in, and then you have a rigid connection in which you can transfer in the entire plastic bending capacity of the beam into the column which it's framing into. So you can see from the moment rotation plots we have here some indicative stiffnesses and the amount of moment which can get cranked in for these different connections. One thing to note is at the flexible, sort of the simple connection where we are allowed to sort of have some rotation, we can carry some moment across there just simply because we're going to connect on the web, but it's not going to be anywhere near what a rigid connection is, which you can see at the top of the diagram. So what I want to go through next is just some examples of what this construction looks like. So the first one's going to be a simple connection. So with these simple connections, they're typically bolted on the flange, and then there'll be a small plate coming out from the column, and you can see those connections there. The big thing to note and how you can delineate whether these are a simple connection and they're flexible and effectively pinned is that the flanges are not connected. So in an I section, the majority of the bending stress is going to be carried at the flanges, and so if those are not connected, then really all we're doing is predominantly transferring shear, and so we have a nominal pin connection. As I said, there will be some moment which is transferred through there, particularly as you get to deeper and deeper beams, but compared to the rotational stiffness that you'd have if you connected up the flanges, we can say this is effectively pinned for design purposes. Looking at a semi-rigid connection, we've got two examples here. So the one on the left, if you look at the connections, these are bolted on an end plate through there. So because the flanges are welded onto the end plate for this example, well, there'll be some moment capacity which can be carried through there. But the stiffness of that connection is going to be dependent upon the thickness of that plate, the stiffness of those bolts, and really whether you can develop the full moment capacity of that beam, and you're probably unlikely given that connection. So this is why it would be considered semi-rigid, and that's how it would get analyzed and designed. On the right is an example of a sliding hinge joint, which is a novel connection developed at the University of Auckland by Charles Clifton, and it is intended to effectively rotate about the top flange, and so you have a low damage design and useful for seismic applications. And then there are some applications with this which also have some self-centering, but again, because we can transfer some moment, but it's sort of that in-between state between fully fixed and fully pinned, it's going to get analyzed as a semi-rigid connection. And then finally, rigid connections are quite easy to pick out, where you see the flanges are fully welded up to the column, everything's beefed up so that we can carry that full moment capacity of the beam into the column. So that's our overview of our connection types. Now the final thing I want to look at here is what's called composite construction. And so what is composite construction? Well, I've got sort of a little diagram which has, what is composite, what is not. So we'll look at the left. A non-composite section is, say, if we have a concrete floor and it comes as a series of slabs, and we just lay those onto our steel, and we have no physical connection between the steel and the concrete. Well, that means that we can develop some slip in between there, so we have no shear capacity across. And so those two sections act effectively independently. The steel beam just sees that concrete slab simply as a load on it. The concrete slab is simply there to span across between two steel beams. And that's reasonably common, particularly if you use a precast concrete floor. But what it means is that, you're going to need a slightly bigger beam in order to carry those loads. If you look at a composite construction, well, say we link up that floor and that beam, and we have some shear studs in between, which are these little sort of mushroom looking things which are sticking out of the top flange of the beam. Well, now all of a sudden we have some shear transfer through there, and now we have that an effectively deeper section, and we can take advantage of some effective width of floor either side of the beam, and now we have a much bigger, we've sort of tricked the beam into thinking that it's much bigger than it is. And the upside of that is we get some significant increases in both stiffness and strength. So stiffness is one of the big ones where we get sort of 3-4 times the stiffness. That means that we can have shallower beams and still not have floors which are vibrating and lively and uncomfortable to be around. And then we can also take some advantage of strength, and that often means that we can get a slightly longer span. Now, really effective way, and that's why they're used so often. So I'll show you a couple of examples of both composite and non-composite next. And so if we look on the left, our composite construction, this is a parking garage. We'd have the decking, so I've got the red arrows on the direction which it's spanning, and you can see that it has these ribs here, and above the top flange of the secondary beams, we'd have those shear studs, so those sort of steel mushrooms which are welded onto the steel beams, and then the concrete of the decking is cast together, so that ties all of this together. Now, because the decking is running perpendicular to the secondary beam and parallel to the primary beam, it actually is not providing any composite action with that primary beam. It's really there stiffening up. And so if you think about from a tributary area and a load path perspective, it's going to go from decking, secondary beam to primary beam, and then obviously into the columns. And we'll have that same load path for our non-composite construction here on the right, except for we just won't be able to take advantage of that stiffer and stronger secondary beams. So you can see, and we know that this is a non-composite element because it has clearly some precast concrete units. I believe these are hollow core units, and so there's no good way to effectively tie those into the secondary beams and get any composite action out of that. So when we do composite construction, we do have to have some considerations when we're designing them, and we have to think through all of the different stages of construction because it means that our system changes as we go. So the first thing we need to do is obviously we're going to erect the steel and put that up and put down the decking. And with the decking, well, it's got to carry its own self-weight and any construction load, so that's, accounts for being able to stack, reinforcing steel on there or lay down any materials that, might be needed. But the big thing is, and what we will see in a lot more detail when we start looking at the design of beams in bending, is that the restraints of the secondary beams are only going to occur at the points of attachment to the primary beams until we get that decking in place. And then we have the ribs of that decking can help provide some lateral restraint to the secondary beams. Once we do that, then we got to pour some concrete. Now, it's really the wet concrete is going to be our main load on the steel. And, with that, because the concrete's wet and it's a fluid, the fluid has no shear strength, and so we can't have any shear transfer across there. So we have to actually design those steel beams, the secondary beams, as beams alone, carrying just the weight of that wet concrete. And it's not until that concrete cures that we can take advantage of that composite action. And then our design case for there would be our full imposed loading on there. And the nice thing is that as that concrete has secured, it provides full lateral restraint to all the beams which it's tied into, both primary and secondary. So I've got just an example of some composite construction. This is the engineering building at the University of Auckland, building 405. One of the advantages to having an engineering building and as a structural engineer is it was designed to have the structural system really shown. So it's got true pin joints at all of the beams, and the braces are all visible. And it's quite a cool structure as a structural engineering professor to be able to work in. And one of the neat things here is they kind of came up with a semi-novel, at least for steel construction in New Zealand at the time, way of working where they would do 3 stories at a time. So you can see the columns would go up, and then they put the steel frame up, but then they would actually, instead of going from, the bottom up, they'd start at the top floor, work their way down, and you can see that in some of these different stages in the photo present, where they'd lay down the deck and then the reinforcement and then pour the concrete on the top floor, and then they would work below that. And what that allowed them to do is that top floor would essentially act, one, to help keep some of the weather off of the bottom 2 stories, but it really provided a lot of protection for the workers below for when cranes and stuff were moving around, and so they didn't have to worry about, the risk of things falling off of a crane. And so you could put more people on there and work safer, and that allowed them to actually progress through this building very quickly, and about 50% of the time from sort of how they had been traditionally doing that. And so we just have another photo here where you can see sort of that different staging of where they've got the decking on the floor below, but they haven't poured the concrete yet on that. So just kind of wrapping up with what we've learned in this video. First thing we looked at were the 2 main structural forms for in NZS 3404 for the steel design in New Zealand, these being the braced and sway system. And remember that those are going to be dependent upon sort of what type of second order effects. Remember, second order effects are these Pdelta moments, where the brace system is just going to be this buckling within the length of the member, and so it's going to be a member type failure that we're checking for and designing for. And that for a sway system, it's dominated by these P big delta, so these are the total story drifts, so story movement, and so we're looking at a story by story failure. And that's because the column ends are not restrained in a sway system, and they can sway sideways. The next thing we looked at are connection types, and remember those are going to be based on flexural rigidity and the ability to carry the moment from the beam into the column. So everywhere from a simple, so a flexible connection, which is a nominal pin, which really doesn't carry any of the moment in, all the way up to a rigid connection where we can generate the full plastic moment at the connection of the beam and generate that into the column. And then finally, the thing that we looked at was composite construction and sort of its benefits around an increase really in strength and stiffness, but that we, because of its construction methodology, we do have to consider each of these different stages as we design to make sure that, you know, our loads are considered correctly, as well as the restraints to the ends of the beams and along the length of them. So with that, thanks for watching.